Hey Tyler.
Hi Dr. Godes.
Welcome to the post-class recap on redox chemistry and solution stoichiometry. Before we get started with the redox chemistry though, I wanted to remind people about a couple things about elements and ions. There are only a couple forms that elements can be in. Right? When we have it in the elemental form, meaning it's not bonded to anything else, it has no charge. For metals, they're going to be solids. For most things, they're going to be solids. There are some elements that when they're with themselves, they form these kind of clusters. So oxygen, when it's only with other oxygen, elemental oxygen, O2, and it's a gas. Right? If copper is with something else, it's not going to be neutral. It's going to be in an ionic form. And so copper can be in the 2+ form. Turns out copper can also be in the 1+ form. Right? And so we don't have that many choices. It's going to be in one of these forms in a chemical reaction. And a lot of times, it'll be in one form on one side of the reaction, another form on the other. That's chemical change. Right? For oxygen, well, when it's in its other form, i.e. in its ionic form, it's going to be 2-. Now, I didn't put AQ next to this oxide ion. Do you have any idea why I might not have done that?
Perhaps when it's in water, it is a different ion.
Okay, so one thing is that if I actually added oxide to water, it would turn into hydroxide. The other reason is that from solubility rules, we know that oxide, if you review them, isn't soluble. It's in the other category, not soluble. And so you're never going to see an aqueous oxide ion. But instead, what happens is the oxide finds a partner. It finds something that has a positive charge, and we end up with copper 2 oxide as a solid, right? And so oxygen, if in a reaction it makes oxide, it's going to find a partner and form a solid or a precipitate.
Okay, so now we know the difference between elements and ions. Okay?
Right, and we're going to use that to predict redox chemistry, right? We learned in class that redox reactions are transfer of electrons, and a lot of times we can track electrons by looking at the charges. Sometimes we can't though, and we'll talk a little bit about that, right? So there really are 3 different cases that we're going to look at. When a metal reacts with a metal in a redox reaction, with a metal reacts with a non-metal in a redox reaction, and when a non-metal reacts with a non-metal in a redox reaction. Right, so let's start with this metal-metal reaction. Well, here we have zinc in the solid form, iron in its aqueous form. If these two react, well, the zinc can't stay the same, right? So it has to flip to the other form. So we could write as a product, what's the other form of the ionic form of zinc?
It's 2.
Zinc
okay.
2+. Okay, so we have one product, zinc 2A+, aqueous. And that's an oxidation because it lost electrons to go up to 2+, and in fact, it lost 2 electrons because it went from 0 to 2+. Well, if this was oxidized, that means that the iron 3+ has to be reduced.
Right.
And so, what are we going to write as its product over there?
Right.
If it started out as aqueous, probably, if it's reduced, if metal ions are reduced, what form do they go to?
It's probably going to become a solid.
It probably is going to go to the elemental form.
Right.
And so we can write Fe solid.
Right, there's no charge on the solid.
No charge on the solid. How many electrons did that take?
Well, that gained 3 electrons because if it was 3+, you'd have to add 3 negative charges to get a neutral charge.
Exactly. And so the number of electrons lost has to equal the number of electrons gained. And we have 2 there, we have 3 there, and so we need to match that up using the stoichiometry. And so we can do this simultaneously, right? Voila. And so now 3 times the 2 electrons is 6 electrons lost, 2 times the 3 electrons, 6 electrons gained. Cool.
Right. Okay.
So our next example, metal plus a non-metal. So we have zinc and sulfur. And I'm not putting S8 even though I know it really should be S8 in the elemental form. I'm just simplifying it a little bit. those at home, you can do it with S8 and bring it to class. So, a metal reacting with a non-metal. Well, what kind of a compound do you get when you take a metal and a non-metal and put them together?
You get a molecule.
A molecule? Do we get a molecule? I think a non-metal and a non-metal, we get a molecule, a molecular compound. But a metal and a non-metal, we get an ionic compound. Okay. So, again, zinc, if it's going to react, what form is it going to end up over here?
Right, so we get the ionic form of zinc again.
Yep.
So we would get zinc 2+.
Zinc 2+. And sulfur, that's a non-metal, and so when it reacts, it's going to form its ion. Okay, and so that's kind of the first step of that reaction. But whenever you have a metal and non-metal reacting, you have to ask the question, is the product going to be soluble and aqueous, or is the product going to form a precipitate or a solid? And you probably don't have the precipitation, the solubility rules memorized, but alkali metals are soluble, nitrate is soluble, ammonium is soluble, sulfates are soluble, chlorides, halides are soluble. Everything else is not soluble. And so sulfide isn't really on your list, and so that means that most compounds with sulfide are insoluble. So these actually don't stay aqueous. They find each other, find partners. Voila, like magic, we get zinc sulfide solid. And since it's 2+, 2-, those charges are balanced, and I don't have to mess with the coefficients at all. Now the last one is when a non-metal reacts with a non-metal. Well, these are actually hard to predict in redox chemistry, and I don't think we'll ask you to predict any of them because when a non-metal reacts with non-metal, we're not getting ions. We're not getting ions. We're getting a molecular compound. And so what I know is that when these react, I'm going to get SOX. Some compound with sulfur and oxygen mixed together. And it turns out for this particular one, I happen to know that the main product is SO2. You actually get a little teeny bit of SO3 in there, but not very much. And like I said, there's no way really to predict, for you to predict what the product is. It's just one of those things that comes with experience. But what you can know is that non-metal, you're going to get a molecular compound, right? So you don't write ions in that case. So for the solution stoichiometry, one of the things we asked you to do was to draw a concept map or a road map for solving stoichiometry problems. And these are basically the two different types of maps I saw students write up on the boards. And the one is kind of organized based on the balanced equation, molarity times volume to give you moles of A, you multiply by the ratio from the balanced equation to get moles of C, divide by volume to get back to molarity of C. And the other one is basically using dimensional analysis. You start out with a volume, you times by molarity, the liters are going to cancel out, you times by the ratio, the A is going to cancel out, you divide by the volume, and you're going to get to molarity. Right? These are both perfectly valid ways of doing exactly the same thing. But the point is that you just have to be organized. So whichever one works best for you is what you should use. Organization is key because as the semester goes on, you'll find we're going to be asking you to do more and more complicated stoichiometry problems. Like the next chapter is gas laws. And so we're going to have moles of gas. Well, how are we going to calculate moles of gas? Through volume and pressure and temperature, right? And so that's going to be another way to get to moles. Always got to get to moles, use the balanced equation to convert to moles of what you're interested in.
Right, and then get to whatever the question is asking for.
Yep. Good. So that's it for the recap. See you in class.